What if I told you that with just one small sensor, you can measure tilt, rotation, movement, and display it live on a tiny OLED screen, like a professional instrument? It can even tell you its own internal temperature. And yes, today we are building exactly that. This is not just a sensor project. This is your first step into robotics, drone, and motion tracking systems. In this project, we are using MPU6050 with Arduino and OLED display. This sensor gives us two powerful outputs, acceleration and gyroscope data. And instead of just reading values, we will test how accurate, stable, and responsive this sensor really is. So let's get started. We will require the following components for this project: Arduino UNO, MPU6050 sensor, SSD 1306 OLED display, breadboard, and some jumper wires. The MPU6050 is a 6-axis motion tracking sensor that combines a 3-axis accelerometer and a 3-axis gyroscope in a single chip. The accelerometer measures linear acceleration along the x, y, and z axes, while the gyroscope measures angular velocity or rotational movement around the axis. This sensor is widely used in drones, self-balancing robots, gaming controllers, smartphones, gesture-controlled systems, and motion tracking applications. The MPU6050 communicates with microcontroller using the I2C protocol, making it easy to interface with Arduino, ESP32, Raspberry Pi, and other development boards. It consists of the following pins: VCC power supply pin, connect to 3.3 volt or 5 volt, depending on the module. Ground pin is connected to the ground. SDA serial data pin, used for I2C communication. SCL serial clock pin, used for I2C communication, connects to the SCL pin of the microcontroller. XDA auxiliary I2C data pin, used for connecting external sensor. It is generally not required for basic projects. XCL auxiliary I2C clock pin, used with XDA for external sensor communication. AD0 I2C address selection pin. When connected to ground, the sensor address is 0x68. When connected to VCC, the address changes to 0x69. ENT interrupt pin, used to notify the microcontroller when specific event occurs, such as motion detection or data readiness. Before we touch a single wire, let's understand one concept that makes this whole project click: I2C. I2C is a communication protocol that lets multiple devices talk to your Arduino using just two wires, SDA for data and SCL for clock signal. Now here is the magic part. Because it is a shared bus, both our sensor and our display can use the exact same two wires. They don't interfere with each other because each device has its own unique address. The MPU6050 lives its address 0x68. The SSD 1306 OLED lives at address 0x3C. Different address, same wires, zero conflict. That's why the project only needs 4 wires per module instead of nest of connections. So here is our wiring. Arduino 5 volt goes to both modules VCC. Arduino ground goes to both modules ground. Arduino A4, that's our SDA pin, goes to both modules SDA. Arduino A5, our SCL pin, go to both module SCL. Install the required library. Before we upload the main code, and this is something a lot of tutorials skip, run an I2C scanner sketch first. This little sketch just scans the bus and tells you what address it finds. If it finds 0 x 68 and 0 x 3C, perfect, you are wired correctly. Move on. If it finds nothing, stop right here. Because that means it's wiring problem, not a code problem. And debugging code would not fix a loose wire. This one step save you so much frustration. Now let's upload our main code. I perform several tests to check the sensor. Accelerometer static test. At this position, when the MPU6050 is placed flat on a stable surface, the acceleration values should behave approximately like this: AX near 0, AY near 0, and AZ around 9.8 to 10.2. During my testing, the Z-axis value remained between 10.1 and 10.2, which is completely normal. Small variation occurred due to sensor calibration, manufacturing tolerance, temperature changes, and measurement noise. Why does this Z-axis show the value? Because the gravity is constantly acting on the sensor. When the MPU6050 is lying flat, most of the Earth's gravitational acceleration is measured along the Z-axis, while the X and Y axes remain close to 0. If your gyro values are bouncing around a teeny bit, even when it's still, that's totally normal. That's called zero offset drift. Every sensor has it. This test checks gravity detection, calibration accuracy, noise level stability. If values fluctuate too much, that means sensor noise or poor filtering. Tilt response test. Now slowly move and tilt the sensor in different direction. During this test, I move the breadboard left and right, and then forward and backward. As the sensor moves, the accelerometer values on the X and Y axis begin to change because the orientation of the sensor relative to gravity is changing. Moving or tilting the sensor to the left and right causes the AX value to increase or decrease. Moving or tilting the sensor forward and backward causes the AY value to change significantly. The AZ value also changes slightly because the direction of gravity relative to the sensor change during movement. Test 3 Flip test. Now I am going to flip the sensor completely upside down. Watch what happens to the Z-axis acceleration value. When the sensor was lying flat, the AZ value was around positive 10.1 to 10.2 meter per second square. As soon as I flip it upside down, the AZ value changes approximately minus 9.1 to minus 9.3 meter per second square. This change from positive value to negative value shows that the MPU 6050 is detecting the direction of gravity. The sign changes because the Z-axis is now pointing in the opposite direction. This is very important test because it confirms that accelerometer is accurately measuring orientation and gravity rather than producing random values. If the sensor were not working correctly, we would not see the clear transition from positive to negative acceleration on the Z-axis. Test 4 Rotation test. As I make small movements, you can see the Gx, Gy and Gz values responding immediately. The value increases when the sensor is rotating and then return close to 0 when the movement stops. Since I am only making a gentle movement, the gyroscope values remain relatively small, which is exactly what we expect. If I rotate the sensor more quickly, the value would become much larger. This test demonstrates that the gyroscope is correctly detecting rotational motion in real time. Unlike the accelerometer, which measures tilt and acceleration, the gyroscope measures how fast the sensor is rotating around its X, Y and Z axis. The fact that the value changes instantly when I move the breadboard and return close to 0 when it becomes stationary confirms that gyroscope is functioning correctly and responding to angular motion as expected. Finally, let's take a look at the temperature reading provided by the MPU6050. Along with the accelerometer and gyroscope, the MPU6050 also contains an internal temperature sensor. On the OLED display, we can see the current temperature being reported in degrees Celsius. In my test setup, the temperature is showing around 33 degrees Celsius, which is close to the room temperature at the time of recording. It's important to note that the temperature sensor is primarily used for internal compensation and calibration of the MPU 6050. While it can give a reasonable estimate of temperature, it is not accurate as dedicated temperature sensor such as the AHT20 or DHT22. Still, it's useful feature because it allows to monitor the sensor operating temperature without adding any extra hardware. Running through these 5 tests mean you are not just looking numbers. You actually understand what the sensor doing and why. And that's it. You just went from a blank breadboard to a fully functional 6-axis motion sensor with a live display. And you can actually understand why it works. Not just that it works. If this video helped you, smash the like button. Subscribe if you are new. And drop a comment if you got stuck anywhere. Thanks for watching and I will see you in the next project.